the next module is going to be discussing limits and what that means for us analytically, which means algebraically and graphically. So we're going to start today with tables and graphs. And first of all, it's important to talk about what a limit is. And a limit is looking at a function and having our x approach a particular value and asking at that point, what is our y doing? And so when the first statement here is just talking about that value that we're approaching, certainly does not have to be defined. It could be a puncture hole, and we could also go up to one of the or down to one of the infinities. The notation for limit, this is huge. I'll star that. We're going to look at that pretty much the whole module. It says the limit of f of x as x approaches c, that should be a c, not an a, equals the number L. So this means as x gets closer to c, but it may not be equal to c, the corresponding values of f of x or the y would get closer to that number. And so first of all, we're going to look at that from a table perspective. And what you're going to do first, you could do one of two things. You could simplify the function by hand. And I know learning from home, you'd probably rather use your calculator. So you're going to do the following. You're going to, I'm going to use my box feature here so that I can fit it for you. You are going to, step number one, type function at y equals, and this is on your graphing calculator, 2, you're going to press second window, and second window is going to give you the table set feature, and then you're going to change the independent variable to ask instead of auto. And this is going to allow you to make choices for what you want to put. So when you do that, then we're going to look at our table here, and we're going to start with these values. So when I plug in a 0.75, I get 2.3125, and a 0.9 is 2.71, and a 0.99 is 2.97, excuse me, 01, and the 0.999 is 2.997. And then we're going to look at the other side here at 1.001, we get 3.003, and then 3.0301, and 3.31, and then 1.25, 3.8125. Now, as we look, and then 1, if you typed in 1, it would say error, which means that's undefined. And if we look a little deeper at our function and we factored out that cubic, we would have a puncture hole there. So we're looking at the limit at a puncture hole. So this right here, coming from this side, these figures, are to the left. The numbers are to the left of 1. So here we are approaching from the left. So this is the left-hand side. If I looked at this graphically, that's what we would be doing. And then this part over here is approaching from the right. And what we're looking for is that we get arbitrarily close to some number. It may equal it, it may not, but taking a look at what's happening, the numbers are coming from the left, they are decreasing and getting ever so close to 3. Or increasing, and getting ever so close to 3. And so what we're after here is the limit as x approaches 1 of our function. And if you notice, coming from the right, we're decreasing, and as we get super close, it looks like that approximate value is a 3. And this is an estimate, but it's something that that we're showing. Now, tables are pretty simple to work with. Now let's focus on the graphing notation. So finding limits from a graph, the limit as x approaches a, this little plus sign right here means from the right. So we're approaching that value from the right-hand side of our graph. And this one right here, the little minus sign, means we are approaching from the left. Okay, so, and those are called one-sided limits because you are looking at them only from the directionality of one side. So what we're going to do now is we're going to look at a function and find the limit from the graph. Because it's piecewise, the boundary value is what we're approaching, and you can see that from the notation there. All right, let's look at, so the first thing is if x equals 0, our y is a 5. So, and I'll graph that for you in a minute, but let's look at this top part right here. If I factor out an x, I'm left with x times the quantity, x plus 1 over x. If those cross out, that means I have a removable discontinuity or a hole at x equals 0. So what we're going to do is look at what's left and then plug in the 0. So at x plus 1, that hole would be at 0, 1. So that means when I graph, I have a hole at 0, 1. I'm going to apply how I would graph up 1 over 1 in that direction, down 1 over 1 in that direction. And when x equals 0, my y is a 5. Okay, now we're going to use that graph to find our limits. So when we're looking at 0 from the right, so I'm looking at this one right here, I go to my graph, I find the right side of my graph. So I'm coming in from the right, imagine I'm walking the curve, and when I get to 0, what is my y-coordinate? My y-coordinate is a 1. That's okay that it occurs on a puncture hole. And this is the left side, and I'm coming in from the left, and my y-coordinate when I hit 0 is a 1. Because the two one-sided limits are equal, this one has no directional sign. This is a two-sided limit. And in order for that to exist, both the right and the left have to be the same. So those are the same, so that's a 1. And we also see here that our limit occurs at a puncture hole. Okay, now moving on, here's another graph. And this one, again, is piecewise. So we're going to graph it first. We know at 1 that the value is 4. And then when we go, starting with a 1, and we go values less than 1, I plug in the 1. 1 plus 2 is a 3, but that gets an open circle from our piecewise days there. And so I'm going to graph like that. And then if I plug in a 1 plus 4, that's a 5. That's also an open circle. And that, remember, is an open circle because the boundary value is not included. Okay, now we are ready to look at our graph. So when I approach the graph, one from the right, this piece is from the right. So coming in, when I hit 1, my y-coordinate is a 5. And the next one is, this is the piece on the left-hand side. So coming in from the left, then my y-coordinate would be a 3. And now the two one-sided limits are not equal. So we say, at this point right here, that the limit does not exist. And we will use this abbreviation, DNE. And the reason that occurs, here's the reason, this is important, the two one-sided limits are not equal. That's why that limit doesn't exist. So here's something else that I'll ask you to do. We're going to look at a graph with all kinds of stuff going on, and we're going to start here at 4. So find 4, okay, find the left side and the right side. So as I'm sorry, that's -4. So over here at -4, almost divided in 2. So it says from the right, here's the right side. So this piece right here, I'm coming in from -4 from the right. So there's my -4. And here's the right hand side. And I would get -1. And then from the left, this would be the left hand side, I would get 3. And again, these two are unequal, so this limit does not exist. Okay, now as we look, we're going to find -1. So here's -1. So find the right side of the graph, and as I'm coming in from the right, which is right here, I'm following along. Once I hit the x value of -1, my y coordinate is a 4. And when I come from the left side and I come up to -1, that's a 4. Both of my one-sided limits are the same, so that limit is 4. Now, the next one, we're going to look at 2. So 2 coming in from the right, my y coordinate would be a 5. And 2 coming from the left, my y coordinate would be a -1. Those are not the same, so those do not exist. And then lastly, we're going to look at 4. So we have the right side and the left side. And when we come in, our value is a 2, a y value is a 2. The two one-sided limits are the same. And so this guy right here was a point. This guy right here was a hole. And again, these two didn't exist because our two one-sided limits gave us different values. And so they don't exist then for the limit coming from both sides.